Corals have been around for a very long time, evolving out of the Cambrian period over 540 million years ago. They have established themselves as the key organisms that drive the ecology of our coral reef systems. With the threat of anthropogenic activity increasing the rate of climate change, and threatening the survival of our marine ecosystems and industries,
unlike most animals, corals do not fall under the centralized Darwinian concept of competition and survival. Corals go through a process of slow change that is known as reticulate evolution. This is driven by the physical environmental factors that facilitate the distribution and behavior of corals. These factors include global circulation patterns, regional tidal systems, tectonic movement, temperature fluctuations, and more.
Just like dandelions, blowing their seeds in the wind, corals use strong surface currents to spread and maintain their genetic connections. Whereas, in weak surface currents, corals become isolated groups, until their propagules can be dispersed regionally. So, we can assume that the ebb and flow of surface currents, through time, have induced changing patterns in genetic connectivity between biogeographical regions. This is known as surface circulation variance, a process for evolutionary change, during the presence and absence of ocean currents, that facilitate dispersion. Recent studies into the characteristic mass spawning of corals in the Indo-Pacific region and Caribbean have begun to close the knowledge gap on reticulate evolutionary processes of corals. As part of the mass spawning phenomena, cross-fertilization can take place, developing what is known as the hybridization of species. Hybridization creates high genetic variation in coral speciation that will have the opportunity to occupy surrounding geographic niches. Subsequently, reticulate evolution and hybridization of corals is a major contributor to its success in widespread distribution. We know that corals have been able to adapt through long, slow periods of biogeological change through differing paleoclimates. So, it is now time to use that knowledge and find out how corals can adapt to changes that are happening right now. The ocean is the largest sink for carbon dioxide we have, and this is helped greatly by the ocean's coral algal symbiotes that sequester carbon dioxide, just like our terrestrial plants on land. But once this sink becomes overloaded, temperature rises, and ocean acidification increases, corals endure bleaching by losing their algal counterparts, giving them a sad, gray coloring that we are seeing on too much of our present-day coral reefs.
So, now we need to understand the significance of reticulate evolution in the success of corals. What biogeological climate are corals currently situated in, and what processes will corals need to endure during this time period? This will allow us to facilitate their success as reef cohorts, maintaining coastal reef ecologies that many of our lucrative industries thrive on. Moreover, if corals are organisms that have been able to adapt to the fluctuations of the Earth's paleoclimates, that is, breaking down and repackaging themselves over and over at the whim of ocean circulation patterns, then we can assume that corals have the capacity to adapt to changes in the present climate through studying their epigenetics, and look towards the possibility of assisted evolution.